In 41, we're going to look at a discrete set, or it's not quite a discrete set, but we're going to look at um, a infinite collection of points that have an accumulation point somewhere, and we're going to try to see to what extent this terminology that we're learning, boundary, open, closed, connected, and bounded, applies to the set S. So let's first get an idea of what S is. So S is we take the imaginary number I, and we take all, well, we divide it by all natural numbers. So if we were to mark I, say up here, that will be one of it. That corresponds to I over 1. But they're also going to get I over 2, and we're also going to get I over 3, and we're also going to get I over 4, and so on. And these they're going to start to get closer and closer together, and it looks like they're converging to 0, and in fact they are. It's pretty clear that the sequence I over n converges to 0. 0 the complex number. And we want to ask what's the boundary of the set? Well, if we focus on any one of the points individually, if we zoom in close enough to them, we can always sort of find a neighborhood about them that only has that point in it. And what that means is that if I were to look at nearby points for any of the green points, there's only, if I'm not allowed to be myself, that is, I'm not allowed to pick the point I'm at, there's only points outside the set. So what that's telling us is that none of the green points are boundary points themselves. However, there is this point here, 0. And no matter how much we zoom in to 0, there's always going to be points that are not green and points that are green. In fact, there will always be an infinite number of green points and an infinite number of non-green points. So actually, 0 is on the boundary of S. And 0 actually is the boundary of S. So, anyway, oops, 0 is the boundary of S. So anyway, it's because the definition of the boundary is, well, every epsilon neighborhood should have points inside S and, in S and outside S. And it certainly does. Great. Now, the next question is it open? Well, there's no wiggle room at each of our points, right? We can only stay at our point and we're not allowed to move from it. So, so none of the points are interior to S, really. So our set is not open. Furthermore, our set is also not closed. And the reason is it's missing this boundary point. 0 is missing from S, and so we can sort of imagine walking along, making hops, walking along the green points to 0. We never are going to quite get there, but we'll get very, very, very close to there. So another approach to saying what I just said is one definition of closed is that you have sort of all limits of convergent sequences, and we don't have this limit. At any rate, this is not closed because we're missing our boundary point. This is also not connected. It's not connected because, well, look at the big gaps. In fact, this has infinitely many components. Essentially one for each point. Is it bounded? Well, every element of S, every element of S has modulus strictly less than, well, I can say less than or equal to if I want, the modulus of I, because we're just taking, we're dividing whatever the modulus of I is by n, so I can say that it's certainly strictly or less than or equal to the modulus of I. And the modulus of I is 1. So all of the elements of S have bounded modulus, so this tells us that S is bounded. I'm going to say B double D for bounded. And this set S, you'll get similar behavior for any set that's made from a convergent sequence where it's missing its limit point.